Okay, so yeah, thanks for coming back. So since today the weather is not that lovely, so I feel less guilty to keep you here. Yesterday we were mainly talking about things which happened like 35 years ago, and so starting from today, I'm going to discuss things that happened more recently. Let's recall things, some newcomers. Let's recall that where we were yesterday. So we'll consider abelian scheme, so a torus vibration, and the one of the very natural operation you can play with it is the multiplication by n, which is so this is a abelian scheme over B, and the multiplication by n is an operator, is natural morphism. So you can choose, for example, n and any n greater than 1. And then we get a weight decomposition. So I haven't told you how to prove that this pullback morphism is diagonalizable, but I'll do this soon. But the main character is to understand this weight decomposition, this is actually a cohomological shadow of so-called Fourier decomposition. To understand this, so this seems to be something very linear, which is only read up from this multiplication by n. But in order to understand this better, the idea we discussed yesterday is that we want to borrow. The first thing we want to borrow is the dual. And so this is f, and then we borrow the dual. So then we want to construct cycles. Oh, hey. Which are quadratic in terms of the Fourier transform. So there is a L, which is a Poincare line bundle. And then we can define algebraic cycles, which I use the letter F, where the F denotes the Fourier transform. So we can define F, which is the total chain character of L, but since L is a line bundle, it's just the exponential of the first chain class of L. And then there's a Fourier, so the L induces a Fourier transform from A dual to A, and there is an inverse Fourier transform, and we can define F inverse. So then we can also define the degree K parts. So this is a degree inverse K. So this lies in, for example, Chao K. I just remember, Chao upper K. I just remember their homological degree. So the upshot in the theory of Fourier decomposition is that this decomposition can really be understood in terms of these cycles in a universal way. So let's recall that since from the fact that this induces derived equivalence, we get an expression of the relative diagonal. So the relative diagonal is the psychotheoretic realization of that this phi inverse in composed with phi is identity, but the right-hand side, you can just express things in terms of the cycles with natural cycles pi 0, pi 1, till twice the relative dimension, where every pi a here is nothing but you just, because I mean it's a convolution of these two. So you pick the cohomological degree for the first factor, and it composed with F inverse 2G minus K. So it's really just choose different cohomological degree, which tell you different. So this identity is more or less for free by that this L induces derived equivalence. So which is, but after writing, so this is the identity in the Chao group. And the reason we express these cycles in terms of quadratic relation is because, we borrow the dual, and we have first to go there and come back. And these two will involve the quadratic things in the expression. Okay, but after writing this is more or less for free, as I said. But after writing this down, it's not so clear that this decomposition induce anything nice, because, well, you need the orthogonality of this. So you want to show that these actually are projectors, the orthogonal projectors, which really realize you the decomposition. So okay, so the key. But the upshot is that this turn a property of so whatever property you want to learn for this decomposition, finally it is reduced to a tautological relation between this Poincare-like bundle. So the key relation, which makes everything work, which I call this a strong Fourier vanishing. The following, so the relation is very simple. Let me just write this down. So Fi, Fj composed with Fi inverse. So for F is all. So this is 0 Fi plus J. It's not equal to 2G.
Okay, for a moment, I mean,
sure.
I'm a little bit confused. These F these Fi's are Java graphs in the private product, but it's also thinking of an operator going from Java A to Java A hat, right?
Yeah, you can think this way, yes.
And when you write the composition, you're thinking that.
Yeah, you can take this. It's a smooth one, so it doesn't matter. A is smooth. Yeah, I assume this, yes. Yeah. So yeah, so concerning Michael's question, so you can either think of this as a correspondence and view this as a composition, or it's just a convolution for convolution products for cycles. You have a cycle on x cross y, y cross z, and you can take the composition by pull back to the triple product and push forward to the 1/3 factors.
So you do mean a check.
No, since this is quadratic, so you first go to dual and come back. Yeah. So that's the reason. That's the reason the cycles are of quadratic types in terms of the Fourier. Yes. But every Fk is from A to A check. So these are the child cycles on the relative products over for A and A check. But you do the quadratic things. Okay. So but in particular, this is a wrong direction. So this is also this is happening on A check cross A check because you F is. Because in general, the A and A check are not the same, so it's good to distinguish them. Okay, first, so this is actually a tautological relation concerning different tautological universal bundle, Lie bundle over these abelian schemes, and it's a set of relation for every I plus J, which is not equal to 2G. And first, let me explain why this works. So why, assuming this, so strong Fourier vanishing. Will imply that these pi I are these pi k are they're orthogonal projectors. So to see this, okay, if we take two different k, so then pi k composed with pi k prime, but this is, it's a quadratic here, but so that's f k composed with f 2g minus k inverse, and f 2g minus k prime inverse, and to f k prime, right? So it's just the four terms, and then you control the vanishing of the thing in the middle. So this is 0. Okay, then also if k for the fixed k, then pi k composed with pi k itself, it's just for example, if you consider pi k, it's the same as pi k composed with the diagonal. But diagonal is always expressed in terms of this sum. So this is pi k composed with just the all pi. And then by this vanishing, only one of the terms that survive, which is just pi k squared. So in particular, this proves that once you have these relations, then you prove that this pi k works as expected. So they are orthogonal projectors. So after yesterday's talk, shall we ask me if is there any? So things I said the motivations to do abelianization, namely we want to extend the structures for abelian varieties, the tori, to study the case with singular fibers. And shall we ask me, is there a conceptual reason why when there are singular fibers then the thing works? And well, it's something I don't have a very good conceptual reason, but I have a reason, a technical reason, which is in terms of tautological relations. So, so in the abelian case, then you have so many vanishings, which are listed in these. So for every pair ij which is not equal to 2g, then you have a relation. And when there are singular fibers, as we will see immediately, the relations are not as good as these. There are correction terms, but the correction terms are controlled. So we have mass, but the mass is controlled in a nice way so that the thing still works. I'll explain. Well, so here I'm writing down, these are the strong Fourier vanishing, but later so the thing that really works are the Fourier vanishing, which is weaker than this, but the mass involved in the correction terms are controlled when there are singular fibers. Okay, so these are the key relations. So then let's give you a quick proof, because the proof of since the proof is also quite interesting. Strong Fourier vanishing. So the proof will also first come back to derive the category. Because if we look at this quadratic term, it looks like you consider the k-theoretic interpretation of you start from here and you do phi L and come back as the phi of the relative diagonal. So if you take the wrong degree of the Chern class, so if we pick k, which is not 2g, then so by looking at phi of structure sheaf of the relative diagonal on the dual side, this is equal to phi L composed with phi L inverse, just by taking cycle class. So you get 0 if you pick the wrong degree class, the Chern class, and then this term is I plus j is equal to k, and you have a quadratic relation. Okay, so obviously this is weaker than what we want. We want the vanishing for individual one, but we get the vanishing for the sum of all of them. So then the idea is that we so instead of we try to really directly prove that every individual one vanishes, we cook up relations between these. We find a way to scale every individual terms in different ways, so that after producing enough relations, we get the vanish for individual terms. So the idea is to use the multiplication back. So this is so we consider ID n. So this is a morphism from A cross a dual to itself. And the key property we use is just, so here you have a Poincare line bundle. And then maybe just for convenience, yeah, okay, let me just write this way. So the geometric property finally we use is really just how this Poincare line bundle is compatible with the multiplication. So if you pull back this, then this is nothing but L tensor n. But, okay, so this is just the geometric input at the first place, and after you have this, then then it's a formal calculation. You just so this is a relative product, and you pull back this relation. Well, because but of course it's a relation means something 0. So after pulling back, it's also 0. So this is 0. So this sentence is actually is a wrong sentence because the relation. Anyway, we pull back the relation. So the left hand side is also 0. For the right hand side, since we scale, so this is fj as the j's power of the C1. So then since this pullback scale it by n, so this really I plus j is equal to k. So this really just scale everything by the power, which only depends on the second factor. And you can play this game for any. After that, so since you have a bunch of tautological relations which force you to have the vanishing for individual ones. Okay. So here it seems that so all the nice properties we want is reduced to certain. So the upshot is for any nice properties we want for this decomposition is reduced to the tautological relations between these cycles, and these tautological relations can actually be proven this way. It's a pretty simple argument. I think first due to Bourville. Okay, so after having this, then really we get the decomposition in a universal way. So the universal decomposition. So everything here actually can be expressed using the language of relative Chow motives, but in this talk I will avoid using motives. So, but I just write down the concrete statement, what it means. So why I said this, after you have the decomposition of the relative diagonal in terms of orthogonal projectors, then you get the relative decomposition. So the reason is, so for example, it depends on what generality you want to work on. So if you want to work on the level of cohomology, then, well, obviously you can decompose it into the summons, where this is just, you view this pi k as, maybe I use k to be consistent. So you view this pi k as a correspondence and operator, and you just take the image of it. But this actually can be done also in the level of Chow. When this guy is an infinite dimensional vector space, which is not so obvious that the multiplication by n is diagonalizable, but you just take, once you have a decomposition like this, then you get the decomposition this way. Finally, you can also work everything out in the sheaf theoretic level. So the push forward, this concerns the decomposition theorem for the abelian scheme, and then the decomposition tells you that really this needs a little work, but this is decomposed into local systems. This is the ice. We calculate the ith cohomology of the fibers and shift it by minus I. Okay, so this is this is actually just the realization functors from the category of relative Chow motives. If you care about sheaf theoretic statement or cycle theoretic statement or cohomological statement, they all can be read up from here. And but finally, to check, it's a quick remark, to check this decomposition coincides with the weight. Again, you just use this property of the Poincare line. So because you just check that. So pi k, so this k is really distinguished by taking, finally you take which fk. And then using the compatibility with, you just check the image of pi k has weight k via the multiplication by n. So in particular, finally, as a consequence, all the decomposition is independent on the choice of the n. So you can choose any n and do eigenspace decomposition, but the outcome does not depend really on which n you choose. But the So here, the proof I present is pretty complicated. It's not complicated, but it uses you first borrow the dual side, and you introduce these cycles given by the Fourier transform, and then you use these quadratic terms to express the diagonal. But finally, everything you want is induced by certain tautological relations. Okay, so now I want to move to the case with singular fibers where you can. So as I mentioned at the end of yesterday, so you don't have, now you lose the multiplication by n. So this guy you don't have, and so the remaining of the lectures is to explain how to make that work. Any questions so far? You mean B? The B makes, so everything's relative over B, so B makes things more so if B is a point, then the first one is trivial, right? So it's just this cohomological gradient is just a K. And the B makes things more complicated. You have, so this is, the complexity of this decomposition is really just the Leray spectral sequence for this torus vibration. And this is clearer from the third realization. So if the B is a point, this is just cohomological decomposition. But when B is you have a non-trivial variation, then this decomposes something into a bunch of local systems. So yeah, everything is compatible with cut product with classes pulled back from B. But also here it's so from the eigenspace perspective, you see immediately that this decomposition is multiplicative. It's compatible. So all these decompositions are multiplicative. So it's the decompositions above are multiplicative. In other words, it's compatible with cut product. So if you have a weight K class and a weight K prime class, you take the cut product this weight K plus K prime. Always cut product.
It's not just, it doesn't just preserve the filtration, it preserves the gradient.
It preserves the gradient, yes. But this is something which is too strong to be expected to be true for when there are singular fibers, as we will see immediately. Okay, so now I'm gradually extend things to the locus of singular fibers. So the next case I will talk about is compatible by Jacobians. So let me draw the picture to just as a motivation. So if I'll come back to this next time, but if this confuses you, just forget about it, just ignore it. So our motivation is to understand the things like this for the Hitchin system. So the Hitchin system. So the Hitchin base can be thought of as the set of spectral curves, which are planar, which are curves with planar, locally planar, inside. So these are the spectral curves, which are curves inside the total cotangent bundle of a Riemann surface you start with, and n-to-1 cover over the base one. So then, if you take the most general spectral curve, so then this is CB is smooth, and the fiber is just the isomorphic to the Jacobian variety. And then if you move to the next singular case, then this is something like this. So this is the compatible by Jacobian. And finally, we want to do the most singular ones, which where these curves are not reduced, not irreducible. But today we will, so yesterday we were mainly talking about these guys, and today we move to compatible Jacobians. And in particular, I'll explain how, so how the previous theory works here. So as I said, the slogan is that we can, so when we move to the degeneration of compatible Jacobians, then not everything here works as good as it was, but there's a mass, but we can control them in a nice way. So really the conceptual reason why everything works is from the tautological relation perspective. So we lose part of the relations. I wrote down these quadratic relations between this F, but many of them still are true. And with these relations which are true, we are still able to organize things in a nice way, control things. So, okay, so let's, but too many curves, sorry. Maybe, I want to use C to denote a curve, so I just changed the original notation, sorry for that. Okay, so for if C is a projective, it's a locally planar. The singularities can be locally embedded into C2, integral projective curve. Then you can consider the Jacobian, which parameters degree 0 line bundles on this curve. But also you can consider it has a natural compatification, which is the compatible Jacobian. So here this parameterizes line bundles with a fixed degree. But you enlarge it by considering a torsion-free sheet, rank 1, generically rank 1 torsion-free sheets. So this is a smooth commutative group scheme. This is a commutative group, and this is something singular, and yeah, this is but the locally planar condition ensures that this inclusion Zariski open. So if you consider an arbitrary curve, then of course we still can consider the Jacobian and the compatible Jacobian, but these are usually very terrible. Yeah. Oh, but yes. Thank you. For example, if the curve has threefolding singularities, then there might be extra components. So the complexity of this one is almost the same as the Hilbert scheme of points on that threefold singularity, which is a monster. But now we focus on the planar case, which you can think of this as a local model for this Hitchin fiber. Okay, so in this case, instead of just considering individual, when we put in family, so we consider C to be as a family of curves of this type. And then you would consider JC bar to be the compatible Jacobian vibration. So the fibers, of course, they could be very singular, but the assumption I put is that total space is smooth. Assumed. So total space is smooth. Okay, so we want to work out the complexity of these singularities, and maybe before I write down, so there are two stories I want to discuss. One is So here you can also consider the push forward, the decompensation theorem. And as I explained yesterday, so this is the decompensation theorem of, so it's the right-hand side may even just abstractly, the right-hand side may no longer be local systems. They should be perverse sheaves. However, in this case, the perverse sheaves in the right-hand side is understandable by so-called Ngo support theorem. And this is the first thing we use. We need to use the intermediate extension to replace the right-hand side in some sense. And also on the algebraic cycle level, but this decompensation, which happens in the derived category of constructible sheaves, will admit a lift by algebraic cycles, and the algebraic cycles will also, like we saw in the abelian case, will be given by certain symmetries of the derived categories. But everything would be much more complicated. But the upshot of the remaining of the story today is that these two kind of complexities are matched. So one complexity is the complexity that comes from the intermediate extension and from the perversity structure. The other is from the coherent categories that you want to extend the Poincare bundle to the boundary so that it induces the isomorph derived equivalence. And these two very different types of complexities are matched, as I will explain. Okay, so maybe the first thing, let me just start with the easier part, describing how the decompensation theorem looks like. By the way, so here, so this is just, of course, this is a special case of the decompensation theorem, but it's much stronger than that because this is a canonical decompensation of these two sides, and so that the decompensation is compatible with cut product. And I will explain that this is not the case in general. Okay, so so to describe the decompensation theorem, we can take just delete all the singular fibers and just remember the smooth ones. So then in this case, we know that the push forward is just local systems. And so these are, again, local systems because this is the J, the Jacobian system. And now after filling the singular fibers, the theorem by Ngo, as an application of Ngo support theorem, it tells us that decompensation theorem for, I gave it a name, F, for F from competitive Jacobian to the base is as simple as possible. By this, I mean, if you consider the push forward, now, oh, no, this is not F. Sorry, F is the one from the Jacobian. If you push forward the constant sheaf of the total space, then as we know, it's the right-hand side no longer you no longer get local systems or constructive sheaves, but you should expect to get the perverse sheaves. But these perverse sheaves are all just the intermediate extensions of these local systems. So in other words, every summand on the right-hand side has full support. So this is just the intermediate extension of the base B of these local systems. So in other words, you have over some smooth Zariski dense subset, you have the local system, and there is a standard way for extending them to something over the entire base, which are semi-simple perverse sheaves, and that's it. So we don't have other. So everything from here actually are given by the extension of the local systems downstairs. Yeah, but yeah, they're inside here. Spectrally, by definition, they are inside T star of sigma. Locally, so it's how locally it's embedded in. It's a surface singularity. Yeah. Yeah, or analytic locally, it can be embedded into C2. Okay, so this identity shows that by Engels support theorem, that the sheaf theoretic decomposition of the right hand side is although it's becoming more complicated than the smooth case, but still it's controlled. It's written down very concretely from 6 operation and these local systems that are understood. So just write a cartoon for this. So you have the B. So this is the entire B. And the B, this is the smooth locus where you have a bunch of local systems here. And there is a canonical way to extend this sheaf theoretically the local system to intermediate, using intermediate extension to get purpose sheaves on the entire base. So the theorem, the first theorem, after after introducing this, I want to describe as this is in joint work with Malik and Ying. Also, this is last year, which is an analog of the Beauvais decomposition theorem, the theorem that I just erased here in this setting. So there are 2 parts. The first part is that now there exists the relative decomposition of the diagonal by 2G, where G is, of course, the relative dimension as before. So this is a diagonal into idempotent projectors which happens, yeah. Now we are considering singular spaces, so it's in the lower Chow group. Dimension of J bar and J bar cross J bar over B. Which realizing a decomposition theorem. I mean this one. So in other words, there is a way to decompose the relative diagonal into a bunch of algebraic cycles, which are orthogonal projectors, such that every perverse sum on the right-hand side is really just the reflection of the one of the projectors. So in other words, moreover, each I k can be described by the Fourier transform, as I will explain in this setting. Okay, so this is the first part of the theorem, and then the second part. So the first part concerns the decomposition. So the decomposition theorem of BBDG can be lifted algebraically in this setting. The second part is that actually this decomposition is multiplicative, so in a weaker sense. So from this decomposition, we can define there is the induced motivic perverse filtration is multiplicative. So I'm not going to introduce, so the motivic perverse protrusion, as you can imagine, is just the contribution of the first k factors of these cycles. But instead of stating this, let me just state as a consequence of this. So this shows that the push forward complex is multiplicative. So this is the coproduct achieved theoretically for the push forward complex. And as a consequence of this, we obtain that this is compatible with the truncation functor. So if you truncate this to the i's place, and you truncate this in the j's place, the image will be in the I plus j place. So for example, this tells you the multiplicativity of the perverse protrusion for any compatible Jacobian. But if you just look at fiber, then this for any compatible Jacobian associated with the locally planar singularity, then this proves the multiplicativity of the perverse protrusion. So this perverse protrusion actually plays a very important for compatible Jacobians. This perverse protrusion plays an important role. For example, in the study of there's still many conjectures concerning knots invariants, and the cohomology of the compatible Jacobians. And when the curve has planar singularities of the type x to the power of p minus y to the power of q, then Oblomkov and Schender, they use double affine algebra to prove the multiplicativity of the perverse protrusion. But the method here gives a general proof for any planar singularities. Okay, so these are the two statements I want to explain on the remaining of the talk. The first concerns the projectors, as we saw in the abelian scheme case, and the second concerns the compatibility with coproduct. But okay, so you might be wondering why here I'm only do things at the filtration level instead of the decomposition level. Because in the abelian scheme case, but these are the decomposition can be thought of a generalization of the eigenspace. So you have the resulting decomposition, no matter which category you're working with, is multiplicative. But here, so I'm only stating things in the filtration level. The reason is that this is the best we can obtain in some sense. So let me write a remark. The first remark, this is actually a result by Yonghan Bei, Malik, myself, and Ying this year, which says that so the remark is that the eigen space perspective as in the abelian scheme case cannot work even when the simplest singularities show up. So more precisely, so what's the simplest singularity we expect is the following. We consider MG less or equal to 1, which is the locus of the one nodal integral curves. So here I only allow my curve to be, so this is the open stratum of MG disjoint with the locus of the smooth divisor consisting of curves with one node, and then over which we can consider the compatible Jacobian associated with this. And this is the simplest example we get. I mean, for the degeneration of abelian variety, we can take, but the theorem is that there's no. The theorem is that there is no splitting of the homological perverse filtration can be compatible with the cup product. First of all, and the second, I will not explain more about this, but just just let me just state the result in case it makes sense to you. So there's no SL2, no Kuhneman type SL2 triple. So Kuhneman showed that for an abelian scheme, you can construct an SL2 triple acting on the cohomology with the E operator, the raising operator given by the cup product with respect to some relative ample. But there's no chance to cook up an SL2 on the cohomology of, even in this case, with the E operator given by relative ample. And also in particular, the first part says that no matter how you split the push forward complex, there's no chance that the decomposition itself is multiplicative. It's just even so. This requires, I think, for G. This requires for G at least 3. So the proof of this actually involves a careful study of the so-called double ramification cycle relations over the MG bar and cook up some constraint, some contradiction, which leads to some contradiction to those theorems. But the outcome is that I think the more important thing is the results themselves. That when there are singular fibers, many things are different. Okay, so these are some negative results, but now I'm moving to the positive direction, and want to use the last 12 minutes to explain what really works. Okay, so before I move on, let me first discuss the difficulty. This is remark 1 and the remark 2. It's the challenge for constructing the projector. Constructing the projectors. So we are always sometimes we are in a nice situation where we consider a vibration F, but if we shrink our base to some open subset, then this can be smooth. For example, we just delete all the singular fibers. So sometimes we can shrink ourselves to a Zariski dense so that the vibration is smooth. But the upshot is the challenge is that assume we get the orthogonal projectors pi k over xu cross xu over u. So I mean, for example, in the case of compatible Jacobian fibration, we do have, if we delete all the singular fibers, then we really already get the cycles here. But if we take, but the most natural way for getting cycles on the total space is you just take the Zariski closure to close things up. But this doesn't work. But taking the Zariski closure, mostly are the wrong cycle, are not the correct cycles. For example, as I mentioned, this pi k satisfies some orthogonal, satisfy nice orthogonality relations. There's a bunch of relations between this pi k, and if you just close them up, these relations are all broken. So which means you really have to study carefully what happens on the boundary, and to make sure that these cycles are the right one. And on the other side, on the other hand, the behavior of the cycles on the boundary should be matched exactly with the complexity of the extension using perversity structures from the decomposition theory. Yeah. Yeah, that's right. Yeah.
There are no canonical representatives.
So you just pick a representative of it and take the closure. I think this is well defined. This is okay, but the relations are all broken. The cycle class is well defined, I think. Yeah. Any questions? Yeah. You mean how? Yeah, this is an sorry, I just erased it. Yeah, this is an ghost. Yes. Yeah, it's here. Yeah, so this is very mysterious. From the decomposition theorem perspective, everything is obtained in a nice way from the local systems, from the open locus. But from the algebraic cycle, it's much harder. Yeah. This is the subtlety of particularly the difficulty of the Cauchy-Hanamura conjecture for lifting the decomposition theorem into algebraic cycles. Yeah, exactly. Okay, so now let's try to solve let me describe you the solution to the problem last 5 minutes, and I'll prove give you the details next time. So the solution is, again, okay, so previously the lesson we learned from the consideration of the abelian scheme is that even we are interested in abelian scheme A, we should consider its dual. And we should play with the cycles that are obtained from the symmetries of the derived categories, and we can try to do the same thing here. So we use the idea of duality. Okay, so now in this case, let me start with the slogan. So in any case, you expect that if you restrict yourself to the smooth locus, then these should be the cycles we saw earlier today. The Fi inverse 2F, sorry, this quadratic terms. But now really the question is how you should extend it. But the slogan is that if you want to just extend these cycles by taking closure, they are the wrong objects, and the right objects is that you should extend things which have a richer structure upstairs. So extending. So keep in mind that originally pi k are from the derived equivalence, the Fourier-Mukai kernel of the derived equivalence. So the thing we should really do is to extend these kernels, extend the sheaf. Extending sheaves is better than, well, just at least for our purpose, than extending the cycles. So in particular, okay, let me describe what's the object we should extend. So now we consider the compatible Jacobian J bar cross J bar over B, and So the easy observation is that if we drop one of the bar by only consider J cross J bar over B. So this is fiber-wise, this is a pair of torsion-free sheaves, but you only consider the pair where one of the factors is a line bundle instead of torsion-free sheaf. Then the Poincare line bundle lives here. So there's a way to naturally, you have a Poincare line bundle defined here. Yeah, let me finish describing. So intuitively, the reason for thinking about it is, if you consider a pair of sheaves EB, FB over some curve, so a pair of torsion-free sheaves over some curve, then you can define a vector space, which gives you the stock of this line bundle by a normalization of just R gamma. You just calculate the cohomology of the tensor of these two. So this is essentially what happens, and then you have to do normalizations by involving some other terms. So, but this doesn't make sense if you consider J bar cross J bar, because these two are if these two are torsion-free sheaves, so the tensor is not bounded. So in particular, this doesn't make sense. But if one of the factors is a line bundle, so if one of the factors is a line bundle, then this makes sense. And then you just collect all these vector space together, and this gives you, this is your L. If one of them is a line bundle. And then a ranking, let me finish in 2 minutes. Yeah, okay, great. About 10 years ago, Arinkin showed that, so this inclusion is the complement, has complement of codimension 2. And Arinkin showed that there exists a common Macaulay sheaf. Let's call this P lives over the right-hand side. Such that first, if you restrict the P to the open locus, this recovers L. So meaning that this is really an extension of the Poincare line bundle, but then the P itself is a common Macaulay sheaf. Secondly, this if you do for Mukai transform with respect to this induces equivalences. So in other words, the line bundle does not really extend to the as a line bundle on the relative product, but the extension should be given by a common Macaulay sheaf, and this common Macaulay sheaf preserve the derived category of coherent sheaves. So in entire proof, the hardest part is to show the existence of such a common Macaulay sheaf P, and Arinkin finally reduced this to the Hyman's isospectral Hilbert scheme in his proof of the n factorial conjecture. So, okay, so just let me write down the last sentence. So Leah, you have to go, right? Immediately. So yeah, you locally embed this C into the locally. So instead of considering compatible Jacobian, he worked with the Hilbert scheme of points on this planar curve, and you embed into Hilbert scheme of points on some surface, and then some similar trick is the BKR construction. You go from the product to the Hilbert scheme by some isospectral Hilbert scheme, and use the common Macaulayness of the correspondence, the isospectral Hilbert scheme. Okay, let me just write down the last formula. So using this P, we can, similarly as before, we can define algebraic cycles, but these are more complicated. So these are, previously, it's just these are lie bundles, so we can just do the, you just take the Chen characters. But now, this P is actually not bounded complex by locally free. This P is not perfect, so we have to use the localized Chen character. We have to go through deeper in Fulton's book to define these classes. But nevertheless, we have them. And the reason for everything work is the Fourier vanishing. Writing on here. So now we do, so these F are just the very complicated cycles from this P, and they are not even line bundles, and you don't have much good control at this code dimension 2 boundary. But so if everyone still remember the vanishing we have at the beginning, now we have this quadratic vanishing, but I plus j is smaller than g. So in other words, if you consider everything is ij, so previously we have the strong Fourier vanishing, the 0 here and the 0 here. But now, once you have singular fibers and you have this P is also felt to be a lie bundle, but then, so we do not have as good as vanishing as before, but all the mass actually are contained in this part. So these could be very messy, but all the mass is just contained here. So and we still have half of the vanishing, and this half of the vanishing makes all the statements concerning the filtration work well. Okay, so I'll go to more details into this, but let me stop here. Thanks. Okay.
Everything you said in the second half of the talk is in the context of a flat family of curves which are totally planar and integraloid with a total space of smooth.
Yes.
Okay. So motivation is to look at Higgs bundles. The Higgs bundles are certainly non-integral curves. So you're going to tell us about those later.
That's for next. That's for tomorrow. Yes. Okay. Yeah. It's a completely different set of techniques. So here, finally, we see that the Fi are obtained from the Arinkin extension of the Poincare lie bundle. But this is actually a very interesting question: how to extend Arinkin sheaf to the entire Hitchin base? So people expected something like this to be true, but to the best of my knowledge, I don't think this is achieved yet. But so we use some other techniques.
By the way, another trivial question is you said if you restrict this to J times J bar, then it's the Poincare line bundle.
Yes.
What if you restrict to J bar times J?
The same.
Okay.
So yeah, it's good. It's good point. So if you consider the union of this one with the other direction, J bar cross J, then this is the complement that's code dimension 3, actually. But still, it's pretty large.
First, back.
You mean what? Which?
I have a nice morphism, that scheme where I reverse the feedback.
Ah, okay, here.
Yes, perfect. Don't hold back.
So yes, I think so. Yes, yes. Yeah. Mm-hmm. Yeah. I would if I just think for 5 seconds, I would say yes, because essentially all the statements concern intersection, just intersection theory. So of this F. So if you have a nice base change, then all the things would work upstairs. But I need to think a little more careful to make sure everything. But I think it's yes, I think it's true. Yeah, I don't see any issue because everything's described in terms of I think 95% is true, but I need to think more carefully. Right. Okay. So the thing I'm worried about is a little worried about is because these cycles, these quadratic ones that I raised, should realize the decomposition theorem. But when the space is singular, the meaning is unclear a little. You have to do IC intersection cohomology complex, but it's not clear that these are matched correctly. Yeah, that's. But for the relation part, it should work. Yeah. Yeah, in general, these are wrong. If but if the this is the conjecture I mentioned earlier. So if the vibration, the Lagrangian, so then you have something like the other half that holds, which makes that's the reason we conjectured that for Lagrangian vibrations, it really should behave like abelian schemes. So for the singularities which showed up in the Lagrangian vibration, and then all the nice properties that's in the Beauvais decomposition story should hold. And so essentially the reason is because you expect to have more vanishings there, but this is speculation. Yeah, we expect we have more vanishing than this, but this is a universal structure as long as for for any family of planar singularities, not necessarily Lagrangian, not necessarily spectral curves, but these relations are always true. And this relation is responsible for having the part A of the theorems I mentioned. But in the special cases, there would be more. And yeah, this is quite actually mysterious, and I hope to understand it better. Like the counterexample, I wrote for MG bar. So universally, that even after putting in the simplest fibers, then the expected properties for abelian scheme just fail. But I would expect everything would be restored if you consider the genus G nodal curves inside the K3 surface for them. So you just restrict the K3 slice and all this. So from the tautological cycle, tautological relation perspective, then you have a bunch of relations, many correction terms, but after restricting to a certain slice, then these are just gone miraculously. And yeah, so. Good question. This is Fourier vanishing, strong Fourier vanishing, same equality I plus J not equal to 2G. So this is the mass caused by the singular fibers, which is also the mass which causes the failure of the split multiplicativity decomposition and so on. Engel's theorem. So far, it's Engel's theorem has not. Yes. One of the steps uses Engel's theorem. But so far, according everything from here, it's just about relations. Yeah, so Engel's theorem is used in the following. Actually, in this pretty soft way is after you constructed orthogonal projectors, you need to show that these are the right. This has the right homological or sheaf theoretic specialization. So this you get some abstract projectors. You want to show these really are the algebraic lifting of the decomposition theorem. But using Engels-Support theorem, it suffices to check this over the smooth locus, which is offered by the Beauville-Denier-Moore's original theorem. What?
It's just started raining.
Okay. Yeah.
Even getting back to the main.
Yeah, we are stuck here. Does it answer your question? Okay. Yeah, we are stuck here anyway, so. Yeah. It's a common Colli sheaf. Oh, yeah, I think you just calculate things over the node, a nodal, just a nodal rational curve. So you can reduce this to, it's something like the ideal sheaf of the node is not perfect. Yeah, in the nodal cross nodal, this P can be written down very concretely. It's not. Okay, thank you.